Hello guys, so we are going to continue the discussion with respect to the Algerian forest fire dataset. We have already done the ED feature engineering, which we saw it over here, and we had created a cleaned dataset.csv, right? That file after feature engineering. So that file is somewhere here. So this is the file that is available. Now we are going to do the model training. We will probably read this particular dataset and perform the model training with the help of linear regression. Then we'll go with Ridge, Lasso, Elastic Net, and I will also teach you something called as cross validation. Okay, all these things we will be doing, and probably it will take 3 to 4 videos, and then we'll do it. Okay, but since you have already learned about simple multiple linear regression, I think you'll be able to understand this also. So quickly, first of all, we'll import all the libraries as usual. The cleaned data set that we probably did after feature engineering, that same data set I'm reading over here. So this is how my df.head looks like. Everything has been converted into numerical or float, but we need to take care of only one of this feature, that is classes, which is our categorical features. Okay. So if I probably go and see df.columns, so this is there. Okay. I don't require this day, month and year because I'm going to just consider this all my independent features, and we need to predict the temperature feature, right? So for that, I'm dropping day, month and year with axis is equal to 1, and then we have done in place is equal to true. So finally, we'll go and see our df.head. Okay. So again, guys, these all are very simple. Okay, don't tell me, Krish, you're going very fast. Since you're practicing from longer time now, I think this you will be able to understand. Okay, please comment down in the discussion forum if you're not able to understand, guys, because I feel if I'm just saying you that we need to drop day, month and year, and just by seeing the column, you will be able to see this, right? We are doing that, right? And we have practiced a lot of feature engineering, EDA, we have solved, I've written the code line by line. Now, trust me, if I probably write all this lines by line again, it will take 40 to 50 minutes, which I can probably complete in 20 to 25 hours. Okay. So yes, please go through the code, try to understand it. We have already practiced. If you're practicing well, you'll be able to understand this code also. So finally, you get df.head over here, with respect to my data set. Now let's go and fix this categorical features that I have in my classes and try to convert this into two labels like 0 and 1. So first of all, df.classes.value counts, if I do, I'll be getting fire, 131 records is there, not fire, 101 records is there. And similarly, fire is also here. It may be with additional spaces, it may be with less spaces. All these things are there. But I just want two categories. One is fire and not fire. So for this, I've already showed you how to do the encoding. Will you say np.where, wherever this classes is basically having not fire, it will basically convert it into 0. And wherever it is fire, it will basically have a label value as 1. So this is what we are going to execute it, and this is what df.tail, I will be able to see my classes as 1 and 0s. Okay. Now if I go and see my df classes.value underscore counts, now I have 137 ones and 106 zeros. Okay. Now as usual, first of all, we will try to divide this as our independent and dependent features. Now in this case, instead of calculating temperature, we are calculating WFI. Okay, FWI, sorry. And what is FWI? So if I probably go and see over here, FWI is nothing but fire weather index. Okay, it's okay. You can take any numerical features and you can do the regression problem. And in this case, what I have done is that I have basically taken FWI as my output feature. So in my independent feature, I have all the independent feature, and I'll just drop WFI column. And this WFI will be my output feature. So here, if I go ahead and write x.head, so these are all my independent features that I'm going to specifically use. And this Y is my dependent feature. So after this, what we do, we basically do the train test split. Then here is my xtrain and xtrain and xtest shape. Okay. Now, if you want to perform feature selection, now this is where we are going to probably learn about feature selection also. Now this is super amazing, guys, because once we do this correlation, right, we'll be able to find out the correlation between all the features to the other features, right? Like like temperature and RH, how it is correlated. It is correlated by minus 0.65. Now how I can use this particular information? Let's say I keep a threshold of 85%. Okay. And I say that whichever correlation, whichever independent feature has this specific correlation of 85%. Okay. I'm probably going to drop that particular column, because see, let's consider this. Okay. And I will just try to explain it to you in a better way. Okay. So what I'm actually saying is that, so let me just write my, come up with my writing pad. Now let's say if I have this input feature and this input feature. Okay. Let's say this two input feature are 90% correlated. So let's say if this is 90% correlated. Okay. That basically means when my temperature is increasing, my this WS value is also increasing. Okay. So when I say 90% correlated, that basically means this and this feature are almost same. So we don't have to take two separate features, right? We don't have to consider this as two separate features. We can drop one of the feature and we can just use this, because these are both 90% of the time, these are like most of the similar kind of features are there, right? So let me just explain you in this way also, so that you will be able to understand. Okay, so let me do one thing. So what I was saying is that let's consider this temperature and any feature like FMFC. Okay, FMFC, these are basically my independent features. Okay, now let's say if this two feature is somewhere around 90% or 95% correlated, that basically means these are very highly correlated, right? Now, if this is very highly correlated, this can act like a similar feature. This will also be a similar feature. This is also a similar feature. Both are one and the same. So I don't have to use two separate independent features. I can directly drop them, right? Now, someone may be asking like, Krish, how do you decide 90% or 95% or 85% correlated or minus 85% correlated? How do you specifically decide? When I say minus 85, it can be minus 0.85, right? In Pearson correlation, your values will be ranging between -1 to +1. So who will decide this threshold? This threshold is decided by the domain expert. Okay, the domain expert will be telling that, okay, if these two features are 85% correlated, you can drop one of those feature, right? And this domain expert will only come when you probably work in a use case for a longer period of time, right? So what we do over here is that with respect to this particular correlation, I will go ahead and apply the correlation and check for multicollinearity. And this is what multicollinearity is. What is multicollinearity? Multicollinearity basically means that if I have a X, let's say if I have two features like this, if I have multiple features, so let me just go and write. If I have features like F1, F2, F3, and let's say this is my output feature Y. Now, multicollinearity basically means that if I have F1 and F2 highly correlated and probably F2 and F3 highly correlated, then what will happen is that if these features are highly correlated, we can drop one of the feature, right? Because these two features behave in the same way, right? Or these two features behave in the same way. So I can drop one of the feature and I can probably just use F1 and F3. So this is a case of multicollinearity. In multicollinearity, the independent feature will be highly correlated. Okay. If let's say F3 is highly correlated to the output feature, I'm fine with this, right? Because this is my dependent feature. This will basically help you to calculate the Y. But what if this independent feature are highly correlated? Then this will be a problem. I can either use one of the feature, no need to use both the features. So this is the concept of multicollinearity. Whenever we find independent features that are highly correlated, then it basically raises the concern of multicollinearity, right? Because I'm basically using multiple independent features like that. Okay. So that is what we are basically going to check over here, right? Now with respect to multicollinearity, if I probably go and create this heat map, okay, obviously I'll be getting this kind of graph. Now here you can see FFMC, how much it is correlated to RH. These all are values, like ISI is correlated to minus 0.72 with RH and all, right? Now here I've written a function. Now see, observe this function. Here, first of all, I'll give my data set and this will be a threshold. This threshold basically says that my independent feature should not be correlated greater than this particular threshold. Okay. If it is probably greater than this particular threshold, I can remove that particular features itself. Okay. So what I'm doing over here, I've given data set and threshold, and here I'm making a set of correlation, column correlation, and I've calculated the correlation of a data set. Okay. Now I am going, see what will happen with respect to data set dot correlation. I will get something like this, right? So if I write df dot, what was my input features over here? So this was nothing, xtrain. Okay. So if I try to search this xtrain.core, okay. So what I'm going to get? I'm going to get this matrix, right? This is the matrix that I'm going to get. This matrix has rows and columns also. So that is the reason I am writing a for loop for I in range of length of correlation matrix dot columns. Correlation matrix dot columns basically means in this way, right? Column by column, right? So once I go in this column, I will say for j in range of I. When I say j in range of I, that basically means I'm iterating through each and every elements in this column. Okay. Then I'm saying that if absolute value of correlation of matrix dot I log I comma j. So I comma j is basically indicating with respect to this particular column, if this is my feature, then this will be I, this will be J. Then this will be I, this will be J. So I'm probably trying to check with respect to all the features, right? And if this correlation is greater than the threshold, okay, threshold, whatever threshold that I'm specifically taking, then I'm going to probably take in that particular column. Okay, I'm going to take that particular column and put it inside my variable column name. Okay, and then I will probably add in this particular set. Okay, so once I probably execute this, you'll be able to see that whichever column with respect to the other column has a threshold greater than the threshold that I'm providing over here. So I'm calling this particular correlation with my extrain data and threshold 0.85. This threshold is defined by a domain expert. Okay, for my case, I've given 0.85. So once I go ahead and execute it, and if I probably see my correlation features, so these are basically my correlation features that basically indicates that BUI and DC are 85% or 0.85% or 0.85 correlated, right? So if I probably go and see BUI, so this is BUI, and if I probably see with respect to DC, where is DC? DC is over here. So BUI and DC is somewhere on 94% correlated. See, 0.94, right? So finally, you can see that I'm getting the correlation features at BUI and DC. Now, one more thing, guys. You may be thinking that there are negative values also. And how I'm handling the negative values over here, I've written absolute, okay? So if I'm trying to find out the absolute correlation, that absolute will basically make any negative percentage to positive also. And finally, we are just comparing that it should be greater than 0.85. And this also includes minus 0.85 also, okay? So this is what we are basically doing with respect to this, and we are able to get the correlation fed. Now what we can do, we can drop this correlation features, right? So correlation features will try to drop because see, this BUI is also correlated to DMC, right? So I don't require this BUI. This BUI is basically related with DC, right? So I may also don't require BUI, right? So over here, BUI can be removed and DC can also be removed. So what we are doing, we are taking this correlation features and we are dropping it from both Xtrain and Xtest. So finally, you'll be able to see that I'm getting a column with respect to 9 features only. Okay. So this is about correlation. Please closely observe this, what we have done in correlation. We are just trying to find out the correlation metrics. If it is greater than a specific threshold value, we are just going to take those specific columns and we are going to remove the columns from the entire data set because this is leading to multi-collinearity. Okay. Very much important. Now, finally, you'll be able to see that we have dropped it. And now the next step is very much simple. We have to do standard scalar on our Xtrain. So we have imported from sklearn.preprocessing import standard scalar. And then we have basically written scalar is equal to standard scalar. And then scalar.fit transform on Xtrain. I've got my scale data over here. And then I'm just doing scalar.transform on Xtest. I've got Xtest scaled. Okay. So once I execute this, if I go and see my Xtrain underscore scaled, so this is my data points. Now, box plots to understand the effects of standard scalar. So after doing the standard scalar, if you probably go and see, I've created 2 subplots. One is 1-to-1 with respect to the box plot on Xtrain I'm seeing, and with respect to the box plot on Xtrain scaled I'm seeing. Okay. So here you'll be able to see before, this is Xtrain before scaling. Okay. So this is Xtrain before scaling and this is Xtrain after scaling. Now see, over here, you had so much difference with respect to the data points, right? That is the reason we should definitely do scaling, right? Over here, the range was completely different, but here you can see the range is almost same, right? Just some outliers is there, but it is fine. But the range is mostly ranging between -2 to 4. But here you will be seeing that the range is between 0 to 100, right? And this is super, right? Once we do standard scaling, now we can apply our linear regression model. Now let's go ahead and apply our linear regression model. For this, I will be importing linear regression. And then we'll go with mean absolute error, R2 square. You can also check mean squared error or root mean squared error. So first of all, I created a object for linear regression. I did fit on Xtrain scaled and Y-train, and I didn't predict on Xtest scaled. Okay. I got my prediction. Then we calculated the mean absolute error. Then we calculated the R squared. This is my mean. This is my R. And then we are also scattering the plot with respect to Y-test and Y-pred. Okay. So once I execute this, this is how I'm getting the data point. This is very, very good. See, in a linear direction we are getting when we are plotting Y-test and Y-pred. And this is what I had actually written in the assumption. If I probably talk about R2 square, I'm getting 98% accuracy, which is good. The mean absolute error is only 0.54. Okay. Now let's talk about the main thing, right? Linear regression model we have already done. But what if I want to go ahead and apply ridge and lasso? So the next one that we are going to apply is basically called as lasso. So for lasso, all I will be doing, if I go and search for sklearn lasso, here again in the linear model, you have this algorithm which is called as lasso. Here by default, the alpha value is 1.0. This alpha is nothing but it is the constant that multiplies the L1 term, right? So this is L1 term controlling the regularization strength. Alpha must be non-negative float that can be between 0 to infinity. When the alpha is equal to 0, the object is equivalent to ordinary least square, like just like a linear regression. Okay. So this alpha value, you can probably iterate, you can select it through different ways. But by default, over here, you'll be seeing that alpha will be 1.0. Okay. So what I will do, I will first of all import from sklearn.linear model, import lasso. Okay. So here I've written from sklearn.linear model, import lasso. Then again, I'll be using mean absolute error, R2 square. And again, please write in the comment discussion forum, why is lasso regression used? I've already discussed in the theory part. Now tell me why lasso is basically used, why ridge is actually used. Okay. You have to probably talk about this particular answer. Please write down the comment in the discussion forum. Okay. So here we have R2 square, mean absolute error. Now I'll go and initialize lasso. We'll do fit again in the same way, X train scaled and Y train. And then we'll do the prediction on X test scaled. Whatever is the X test data, I'll get Y train. And then I will try to find out the mean absolute error, then R2 square. And then finally you'll be able to see this is the output I'm getting. So here my R2 score is 0.94. Okay. Now, why it is got reduced? If you know about lasso regression, okay, you'll get to know. Okay, but first of all, tell me why lasso regression is there. Okay, why it is used. So here the accuracy R2 score is nothing but 0.94. The mean absolute error is 1.13. And here, if I probably plot this Y test and Y parade, it looks in a linear fashion. This is so good. Okay, this was with respect to the lasso regression. Now, in the next video, we will not discuss about cross-validation lasso right now. We'll first of all understand what exactly cross-validation lasso is all about. Okay. Now, see guys, let's say, and this is super important. First of all, we need to understand about cross-validation. What exactly is cross-validation? Let's understand. Now, you know that whenever we probably take a data set, okay. So whenever we have a data set, this data set initially is divided into train and a test data, right? Which we have already done. This train data will further get divided into train and validation data. The train data is specifically used for training the model. Okay, training model. Okay. Now, I will just explain you this everything as such as we go ahead. Okay. Let me just use this. Okay. But when we talk about the validation data, okay, validation data specifically. Now in this validation, what we do is that, okay, so let me just make this point a little bit small. So with the help of this validation data, we will perform hyperparameter tuning. Okay. Now what exactly is hyperparameter tuning? Okay. We'll talk about it. Let's say I have in my training data somewhere around 1000 data points. Okay. Now, if I say cross validation is equal to 5, if I probably say cross validation is 5, that basically means when I'm performing hyperparameter, right? Remember, this is my training data. Okay. Now, when I say cross validation is equal to 5, now I'm talking about the validation data points, right? When I say cross validation into 5 is equal to 5, that basically means my 1000 data points will get divided into 5. So I'll get 200. So in the first instance, for CV is equal to 1, that basically means, see, we are going to do 5 cross validation. Okay. For CV is equal to 1, the first 800 records will be my training data set. And I can also write like this. Let's say for CV is equal to 1. Okay. For CV is equal to 1. The first 200 records will be my training data set. Sorry, will be my validation data set for testing my model. Validation data set. Remember, this test data set is completely different. After we probably train our model, we will test our data set, our model accuracy with this test data set. But when I say with respect to validation, okay, if I'm saying I'm going to do cross validation of 5 times, That basically means my 1000 data points, which is in the training data, it will get divided by 5. So I will have 200 data points. So in the first instance, this validation data that will be selected over here will be 200, and remaining all the 800 will be put into the training data. And we will pass this data and find out the accuracy. So let's say I got one accuracy 1. Then what we'll do, we'll again take the cross validation 2. So CV is equal to 2, cross validation 2. In cross validation 2, the next 200 records will basically be my validation data, and remaining 800 records will be my training data. So here I will take this, I will probably check with my model and I'll get my accuracy 2. Okay, I will probably train my model and probably get my accuracy 2. And then we will go similarly like with cross validation 3. The next 200 records will be over here, and remaining all will be our train data. Then cross validation 4, the next 200 records will be over here, remaining all will be my training data. This will basically be my accuracy 3, accuracy 4, and finally I will go ahead and compute my accuracy 5. Now in this scenario, in every cross validation, I have changed my training and validation data, right? And I got a different accuracy, right? So I'm going to apply linear regression or ridge regression for this data also, for this data also, for this data also, for this data also, and for the final data also. And in every data, you will be seeing that your validation data and your training data is changing. Okay. This validation data is specifically used for hyperparameter tuning. Now, hyperparameter tuning basically means I want to probably check. And finally, if I try to find out the average of all this accuracy, this will be the accuracy of my model. Okay. Final accuracy. So if I try to calculate the final one, so this will be my final accuracy. And this is what we specifically do in the validation. Okay. And that is why we specifically say this as cross validation. Okay. Okay. I'll just make a detailed video probably of understanding what are the different types of cross validation. But in short, for the training data only, we are trying to create a separate training data, a small sample of validation data. We train it with our model, we get a different accuracy. So we get accuracy 1, accuracy 2, accuracy 3, accuracy 4, accuracy 5, and then we try to find out the average of all the accuracy. Okay. So this was it, most about it. Now, if you really want to perform cross validation with the help of Lasso, so here I've used Lasso. So with the help of Lasso, all we do is that I will write from sklearn.linear model. There is another library which is called as Lasso CV. So Lasso CV will make sure that it will apply the cross validation here itself. So if I'm giving Lasso CV and initializing Lasso CV with cross validation is equal to 5, then this X train scaled, right, and Y train, it is going to make 5 different cross validation. Okay. And you will be able to see that if I execute this, right. So here you will be able to see it is with cross validation of 5. If I go and see alpha underscore, this is one alpha. If I go and see with respect to different alphas, okay, alphas, what are these alphas? Okay, forget about these alphas right now. You don't worry about these alphas. Okay. So if I delete this cell and if I try to find out what is my prediction with respect to the X test scale. So I will get my Y pred, then you'll be able to see I can also scatter y underscore pred test comma y underscore pred. And finally, I'll go ahead and calculate mean absolute error and all, and I'll get this all, right? This is perfect. So the accuracy over here I'm getting with respect to the Lasso CV is somewhere around 98%. So internally, we have done the cross validation of 5 times. Okay. Cross validation of 5 times. So if you really want to know more about this Lasso CV, just go and search for it. Okay. sklearn Lasso CV. Okay. So sklearn Lasso CV has n underscore alphas as 100 values, different 100 values. What is this n underscore alpha and all? You can basically check out from this, right? It is list of alphas where to compute the model. If none, alphas are set automatically, right? The epsilon, right? So here you have a number of alphas for the regulation parameter. And here you can definitely see the example, right? So here we are basically doing cross validation of 5. I'm giving my training and test data. So that basically means it divides train and test with respect to 5 different validation. Okay. And we can probably find out the average of 5 accuracy and get the output. Okay. So in short, we have applied by this technique by using cross validation on Lasso CV. Okay. So I hope you were able to understand this and we are able to get the good accuracy with cross validation. Cross validation will definitely give us a very good accuracy. Now in the next video, we'll talk about ridge and then we'll talk about elastic net. And for that also, we'll try to use ridge CV and do the same thing, which I have already written the code. So let's see in the next video.